All right. So we're going to go into a new chapter now, and the chapter is all about counting. Hold on. Let me put this away, hide floating meeting controls. All right, so it's all about counting. And so counting is less me like listing numbers. So it's less me saying like 1, 2, 3, 4, 1,000, 1,001, and so on. That's not the kind of counting that we're talking about. It could be, but the thing we're actually talking about is more like this, of like how many M&Ms are in this jar? And something like that, where how can we estimate, how can we come up with a number for how many of these things? So some of the examples the book has is in a lottery, how many different tickets can be played? So I looked up like the Mega Millions where it's got these 1, 2, 3, 4, 5 numbers with a multiplier. And so each of these numbers has like it can be an integer. How many different possibilities are there to play the lottery? If we're running a sports tournament and we're going to seed the teams, so like first seed, second seed, how many different ways can we seed them? If we are in a race with 8 horses, how many different finishing possibilities are there? So like the first one, so like if we've got horses, let's say ABC, a 3-horse race, then possibility is A comes in first, B comes in second, C comes in third, or it could be C comes in first, A comes in second, and so on, right? There's different possibilities for how this race can turn out. How many are there? Let's see other interesting things. How many passwords can be formed that meet certain requirements? So like if you want a 10-character password and it has to have a exclamation point or a special character, how many different passwords could there be? Those are the kind of questions that we're asking. And so for some, this like is super intuitive. For others, it is not. I remember when I took this class, for me, it was not. There was an ice cream question that I asked you on the first day, and that was actually something that me and my friends like spent like 3 hours in a library study room arguing over like how many ice cream flavors is possible. Uh, so for me, this doesn't come natural. And so we're gonna start to answer these kind of questions. And my big advice for you as you go through this is start small. So if I ask you how many different, like, what's the possibilities for a 10-horse race? And you're like, oh man, first A finishes, then B, then C, and the like we could switch it, and it just like gets ugly really fast. Don't do that. Start small. If I'm looking for how many possibilities for a 10-horse race, start with a 1-horse race, a 2-horse race, and try and generalize it from there. So yeah, the first advice is use smaller numbers. So start small. All right, we'll come back to those. So we're going to talk about 2 main techniques today, one of which is the addition rule. The other is going to be multiplication. And these are things that, like once you learn about them, you're like, oh yeah, like obviously. But we'll formalize them a little bit. And so the addition rule says the number of elements in the union of a finite number of pairwise disjoint set is the sum of the cardinalities, of those sets. That's a lot of words. Let's consider the students at St. Mary's. I want to know how many students are at St. Mary's. And maybe I have an access to like the number of first years and the number of second years, the number of third years, the number of fourth years. Let's give them numbers instead. Right? So if I have access to all of those numbers and they're pairwise disjoint, so like no student is both a first year and a second year, no student is both a second year and a fourth year, no student is both a first year and a fourth year, stuff like that. So they are pairwise disjoint. Then I just add them all together, right? So if there's, let's say it's 300 each. Then that's just 300 plus 300 plus 300 plus 300, and then we get 1200. Right? Pairwise disjoint sets, and there's a finite number of them, right? There's only 4 years. And that's how we get the numbers. So similarly, if we have, maybe we break it down into like the majors. So we have like math majors, computer science majors, politics majors, business majors, data analytics majors. And maybe we also have like undeclared majors. And so if we add up all the majors, because in theory, every student either has a declared major or is undeclared, then that gives us the number of students. This breaks down a little bit as we get into like double majors. And so this is, which leads us into our next proposition, where if we've got, so let's say we have math, CS, let's say politics, and maybe we have 10 math, 10 CS, and 10 politics, but at least one is a double major in CS and politics. And so if we add all of those up, we would get 30, but in reality, we would have like 29 or something like that, right? So we don't want to overcount the number of people. And so if there is some overlap, then we can still find out how many elements, like how many students are there that are math, CS, and politics majors. And so this is, in the book, this is proposition 3.1. The number is not so important, but given finite sets A and B, the cardinality of the union, so the number of things in both, is equal to A plus B. That's fine. So that's what we were doing with the years, but it's not sufficient if there's overlap. And so we have this, but we just need to add a difference where we subtract the cardinality of the intersection between the two. Right? And so that says if there is one student who is both a CS and a politics major, then we would add 10 plus 10 plus 10 minus 1. And that gives us 29 students total. Make sense so far? Okay. There's also something called the complement rule, which says that if we've got a finite universe set and suppose that we have some set A, it's a subset of there, we just say that we're talking about counting, and so this is where we're like, there has to be a finite universe, right? Like there's only so many students who go to St. Mary's College. There's not an infinite number of students. And so for a finite universe, and this, then the sum of the cardinality of A, number of things in A, plus the number of things not in A, is going to give us the number of things in our universe. Again, duh. But this is useful because it can, so we can rearrange this equation as needed. So if we want to know like, what's that? Then we can just move it, subtract it from both sides. And then if we know how many things are in our universe, then that becomes easier to compute. All right, so let's look at a brief example. So let's 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I've got a circle and I want to know how many chords, so a chord being like a line segment connecting 2 points on a circle, how many chords can I draw connecting 2 points on the circle? And so thinking about this, so like let's start just with one of the points. So for 1, I can connect it to 10, I can connect it to 2, 3, 4, 5, 6, 7, 8, 9. And so just if I start at 1, I can draw 1, 2, 3, 4, 5, 6, 7, 8, 9 chords. So 9 starting from 1. And then if I look at 2, I've already covered 1 to 2, so I can draw 2 to 3, 2 to 4, 2 to 5, 2 to 6, 2 to 7, 8, 9, and 10. That's 1, 2, 3, 4, 5, 6, 7, 8 additional. And then if I start at 3, I can go 3 to 4, 3 to 5, 3 to 6, 3 to 7, 8, 9, and 10. And I've already covered 3 to 1 and 2 to 3. So that's 1, 2, 3, 4, 5, 6, 7. And this continues, right? So this will give us, in general, if we have n points on a circle, this will give us the sum of things from 1 to n of that number. So, and that's, if you remember calculus, or maybe we went over it in programming too, k plus 1 times k over 2. Wait, no, that's n. You use k if you're proving it by induction. So this is an example of the addition rule, where for each number, we've got 9 possibilities, right? So connecting this number to every other number. And at each step, we just subtract the ones that we've already done. And so for 1, we've got 9 possibilities. For 2, we've got 8 because we disregard 1 to 2. For 3, we disregard 2 to 3 and 1 to 3, and so on. This is the addition rule. Let me tell you about when the addition rule doesn't work. So I'm going to draw an oversimplified map. And we want to go between 3 cities, or from A to C. And there's a waypoint at B. And there's different ways to get from A to B, from B to C. So let's say there's 3 ways. We'll call it D, E, and F from A to B. And there's 2 ways to get from B to C. So let's call one of them G and the other one H. How many individual roads are there total? Yeah, 5. So we add 3 there, 2 there, 5. Great. Now my question is, how many different routes are there from A to C with no backtracking? Six? Right, and we could list them all. So we could say DG is 1, DH is 1, or DH is 1. EG is 1, EH is 1, FG is 1, FH is 1, right? So we've got 3 options for the first one, 2 options for the next. So in terms of 3 and 2, what is that? So we didn't add them because 3 plus 2 is 5. But 3 times 2 is 6. So here's where we get the multiplication rule. I'm going to convince you one more time that this is necessary. Because let's say we added a 4th city D, and there are 1, 2, 3, 4 options. So let's call one of them I, the other J, K, and then that's an L. And so now to think of how many options there are. So if this is like we start at D, we start with E, we start with F, and then this is we end with G, H. And so we can like expand this where we can say, okay, so for all of these, let's assume that we take I as the 3rd path. So and then we just like repeat that. So those same 6 options, but ending at J. Those same 6 options, but ending at K. Those same, but we end at L, right? And so that gives us how many? So 6 times, well, there's 4 additional options now. And so 6 times 4 is 24. So A to C is 6, which is 3 times 2. A to D is 6 times 4, which is also 3 times 2 times 4, because there's 3 options from A to B, 2 options from B to C, 4 options from C to D. Right? So that's where we got like the 6 times 4. All right, and so this is the multiplication rule. The multiplication rule is very long in the textbook. Do I want to write it out? Not really. Okay. This is on page 186. 186. Okay. Here, I will screenshot this and bring it into the document. So it's a lot of text, but let's read it aloud and talk about it. So if a sequence of k tasks, so like let's choose a route from A to D, needs to be completed in order. So we have to do k things. And so we complete the first task, then we complete the second task, then the third, and so on. And let's assume there's n1 ways to complete the first task. So that's the number of roads to choose between A and B. N2 ways to complete the second task, the number of roads between B and C. N3 ways to complete the third task, and so on and so forth. So at each step, we are presented with, we have options. How many options can I choose? At the second task, we have options. How many options can I choose? The key here is that when we look at how many ways to complete the second task, that is independent of how many ways we can complete the first task, right? So when we're looking at the number of ways, when we're at B, we can take either path, G or H, and it doesn't matter how we got to B, right? We could have taken D, we could have taken E, we could have taken F. None of those options matter at this point. We have two options in front of us. Those are independent of the options that were previously chosen, right? So regardless of how the first is completed, and then N3 ways to complete the third task, regardless of how the first two are completed. So all of our previous decisions don't matter, right? Well, they do matter because we've counted how many ways there are, but the result of those have no impact on the decisions we make now. And so on. So we eventually get to the last task, the kth task, and there's nk ways to complete the last task, regardless of how the first k-1 tasks were completed, right? As we're going to the last city, it doesn't matter which paths we chose to get here. And so the statement of the theorem is there are n1 times n2 times n3 times so on and so forth times nk ways to complete the tasks in that order, right? So at each step we look and we ask, how many choices do I have? And then we go on to the next step. We ask, how many choices do I have now? Next step, how many choices do I have, right? And so this is all about sequences. So if I'm in a sequence where I have to figure out how many options are there, then I use the multiplication rule. All right. The only other theorem that I want to give you, this is really a corollary. And then I will go into problems. And so this is if A is a finite set, and then we're going to have, or no, if A sub I is a finite set for I in 1 to k, then we say that if we want to find the product of all of these sets, the number of things in that product is the number of things in A sub 1 times the number of things in A sub 2 times so on and so forth times the number of things in that last set. So this is just, in mathematical terms, the way that we describe the multiplication rule. So let's say the number of this set is the number of roads that we could take from the first to the second city. This set is the number of roads that we can take from the second to the third city, right? To find out all the different possible options, we may not necessarily be concerned with what are they, but we want to know how many. So that's why we've got the absolute value, the cardinality bars around here. And so we just find how many are in the first times how many are in the second, and we multiply all that together. And that product gives us the cardinality of the Cartesian product of all of those sets. So this is just giving us the multiplication rule in symbols. Questions so far? All right. Let's look at problems. So I'm going to move this down. Let me, there we go. Done. Okay, so I'll show you an example. So this is akin to the racehorse question, where if I have 6 people, so like if I chose 6 people from this room and I asked you to stand in a line, there's options like who stands first, who stands second, and I can have 6 different lines with 6 different orders, and they're all different. And so I want to know, given this amount of people, how many different ways can they form a line? And so the answer to this is, let's think of the different steps that I have to take. So I'm going to choose the first person to be in a line. How many possibilities do I have at that step? 1? Yeah. Okay. So for the first person in line, I've got 6 choices. Great. 1 person is in the line. To add the second person to the line, how many choices do I have? How many people can I pick? 5. 2 people are in the line. Now how many choices do I have? 4, right? 3 people are in the line, so there's 3 people left. So I've got 3 choices. 2 people are in line. No, 4 people are in line. I have 2 people left. So I've got 2 different ways to choose. I can choose person A or person B. 5 people are in line. I've got 1 person left. How many ways, like how many possibilities do I have to pick the last person in line? Just 1. There's 1 person. It is factorial. Right. So in case you don't remember or haven't heard of factorial before, this is not us being super excited about the number 6, unfortunately, although I am always excited about factorials. A factorial of a number n, we write it with an exclamation point, and this is equal to n times n minus 1 times n minus 2 times so on and so forth until 3 times 2 times 1. And we assume that our base case is 1 factorial is 1, 0 factorial is also 1, and we do not consider so we mostly consider the natural numbers, so we do not consider negative numbers. So factorial is defined for the natural numbers and 0, just in case. All right. And factorial ends up being kind of nice for these kinds of problems. All right, questions on this? All right, so we're gonna take the rest of the time. I've got 4 questions, at least I'm hoping to get through the first 2 or 3. These 3 are from your homework, and the first one is not. So I'm gonna have you, maybe I'll put you in random groups and have you go to the board and work on them. So I will show this. I'm gonna pause recording so I can put you in groups.